Hello everyone, welcome to the math course online. Okay, so today we're going to talk about something truly interesting and unconventional lessons which you might not find in most physics department trainings. That's what we call the maximum entropy principle. But this maximum entropy principle turns out to be really efficient and has played a very important role in modern data analysis or even recent machine learnings and everything. And in fact, of course, it has strong and important implications in physical sciences as well. So here is the genius that I would like to introduce to you. That's Claudia Shannon, as you can see here. And Shannon's find out a very interesting way of quantify the abstract notions of information. And it turns out by trying to quantify how many information conveyed through some observation or through the codings, he then write down the correct expressions for entropies. Multiplied by the Boltzmann constant, it turns out to be the most mysterious physics quantities, just the thermal entropy that you learned everywhere in thermal and statistical physics. And in fact, this idea can be further promoted to some other mechanism where some of the prior knowledge is known. For instance, if we don't really know the probability distributions, but only know about its mean or its variance, it turns out if you just maximize the entropy using the maximum entropy principles, you can then find out and derive the resultant probability distribution is Gaussian. So this makes a very interesting connection between many seemingly unrelated approximations in science and provide us a much deeper understanding when information nowadays plays such an important role. So before our class begins, let me grab my tea. Very unprofessional YouTuber. So this is green tea on rocks. Very good for your health. Okay. And so if you have any questions, please just type your question there and let me know. And I will try to basically come to some break appropriately during our YouTube live and then try to respond in real time. And afterwards, if you still have any further questions, please do not feel hesitated to leave your puzzles, questions, comments, or suggestions just right below the videos. Okay, so I will read them. And of course, you can also use the e-learn system hosted by National Tsinghua University. I would also be there to interact with all of you. So let's go back to our lesson today. This is truly exciting. And in fact, there's some truly exciting stuff going on. That's why my Apple Watch is ringing all the time. I'm sorry about that. So that says, let me first try to really bridge the interesting connection, the secret connection between information and probabilities. Is that true that whenever you have a probability distributions, you can always come up with some quantitative description about the information you will gain by performing the stochastic measurements? Is that true? Think about that. Okay. And so I will give you a very intuitive example. Suppose now I give you a secret message. that says the sun will rise tomorrow. I'm not saying the sun will shine. No, I'm saying the sun will rise tomorrow. Well, the probability is almost 1. So your intuitive understanding tells you not much information gained, right? If I just write you some secret note saying the sun will rise tomorrow, and literally it doesn't mean much. On the other hand, if I write something down on a piece of paper and hand it over to you saying the next lottery number is something, 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 in order not to really give rise to troubling confusions, I didn't write down the real number, okay? And of course, hitting the top prize of the lotteries is a rare event. And the rare event is associated with a vanishingly small probability. And in that case, we would say that precious information will be gained. So from here, you probably got this rough idea that is, if the probability approaches 1, then there aren't that many information you gain by knowing the message or by performing the measurement. Okay? On the other hand, if the data, the measurement results, or the message contain a rare event with small probability, then we would say the information content conveyed through these means is huge. Okay, so that should be relatively simple. So here we are going to really write down this very important concept. So the amount of information gained after observing the event something of a random variable xk with probability pk is defined by the logarithm function. That is, it's log 1 over pk. So you can see if pk is truly small, 1 over pk will be huge. Taking log is still a large number. Then you get a lot of information out of it. And if pk approaches 1, then 1 over pk is almost 1. Log 1 is almost 0, basically. Okay? So this seems to be a pretty good way to characterize the information, and be slightly more careful because the information is defined as the logarithm of the reciprocal of the probability. So when you flip it, there is a minus sign in front, and this makes perfect sense because the probability itself is between 0 and 1. If you take log, it will always guarantee to get a negative number. So then taking the minus sign will then make this information we define here a positive amount, which is intuitive and which is also easier to handle. Okay? And this logarithm also satisfies several other beautiful properties. One of the most important properties is perhaps the additive properties of information for two independent events. Suppose now you would like to gain some information about two independent events. Their probability is multiplied together, right? So P1, P2. And so if you use logarithm, then their associated information is additive, because taking log P1, P2 will eventually give you log P1 plus log P2, and thus showing the information is additive. And this is something truly helpful. Okay, and some terminology here. So how are we going to use, what's the base number to use in this logarithm? Well, that depends. So some people use 2, and so that's base 2 logarithm. And so then the information you get would have the unit, what we call the bits. That's what bits means. And if you use a natural logarithm, which is also commonly used in computer science and in physics as well, and then what you got would be basically natural bits, and in short, that's nats. Okay, So you might encounter these two different units when you read papers or some other online articles. So don't be confused. And choosing different base numbers doesn't have any significant implication about the information at all. It's just like choosing different units. And you can actually convey these informations rather easily once you know the base number. Okay. Once you know the information, that's not the confusing part. Okay. So before we march into the information entropy, we already got a very nice question from Mr. Crow. So Mr. Crow asks, what is the label of SK? That's a good question. So for random variables, x, I'm assuming is discrete. It might have different outcomes, let's say x1, x2, x3 to xn. Okay, so xk is just one particular outcome with one particular probability. So try to remember this important fact. So in order to really come up with a quantitative estimate of information, you don't need to know the whole probability distribution. As long as you know the associated probability pk of that random event, you can define its associated information. But that's not all. So that would be like the first level understanding of how you quantize information. Let's then come to the second part. That's typically what we call the information entropy. And I've been struggling how to write this because as a physicist, I should either write this as really just entropy or the commonly used dimensionless entropy. But you know, nowadays, if you look this up on internet or you read through all the computer science textbook, they all use Hx. And fine, so I'm gonna use Hx as Boltzmann. So the information entropy at x is defined this way. It's defined as the expectation value of the information content that we just defined for a particular probability. So we will symbolically write this that since for each event we can calculate its associated information, right? And we just calculate the probability of it. And of course, you can write it out. It's very simple. This I is minus log k, and it is weighted with all probability pk, and that's it. But then this whole expression is relatively suggestive. First of all, this expression was first written down by Boltzmann and later elaborated by Gibbs as the thermal entropies. So they are closely related. And it turns out this close relation is really trivial. The thermal entropy is just directly proportional to the information entropy discovered by Shannon. Okay? So that's the first thing. Second thing is that be really, really careful about one notation subtlety here. That is x. I write it as capital 1, denoting the random variable, not a particular value. That is, hx here is not an argument of a function. It's labeling. It labels the dependence or the functional dependence of h on the probabilities or the random variable x. Okay, so please do not just read this as, oh, okay, this h is a function of x. That's not what it means. That's what it means. So for a random variable, it would have an associated probability distribution, pk, right? And from these pk's, you can compute the average or the expectation value of the information. So basically, what exactly is the meaning of hx? Hx is a measure of the average amount of information conveyed per message. That is, for a random variable, if you just do an experiment and try to find out what the outcomes are. So you might get different outcomes whenever you perform the experiment, right? So what is the average information you can gain per message or per experimental measurement? That would be HX. And then this is not very easy to understand then. You might think if my probability contains lots of small pk's, so then the expectation value will goes up, right? Because log pk minus log pk is large. That turns out to be wrong. Why? Because I'm talking about not the information associated with a rare event. I'm calculating the average information content of a distribution. So that log p or minus log p must be weighted by pk. And once you multiply them together, when pk is small, minus pk log pk is actually a very small number. It's not a large number. Okay, so then this whole concept of average amount of information is not intuitively follow the same trend as we understand for a single event. To elaborate on this part, let me just give you a very, very simple example. Okay, this example is simple, but it plays such a huge impact in modern communications. Suppose now that you have a random variable. You take on 3 events, event A, event B, and event C. And for convenience, I would say that the event A occupies half of the probability, where event B and event C occurs with the quarters probability. Okay, so you add it up, that's 1. That is a properly defined probability. So what with these random variables and what is the associated information entropy with that? Well, we just calculated. Oh, I'm sorry here. I just write this incorrectly. Yes, let me change it. So what one need to do here is just calculating the average values of minus log p. Okay, and so the first term, that is the probability 1/2, and minus log 1/2 is just log 2, and minus log 1/4 is log 4, and PC here again is log 4, and weighted with 1/2, 1/4, 1/4, the corresponding probabilities. And so it's straightforward. For simplicity, I'm using the base number to be 2, so I'm really calculating how information can be communicated, transmitted through the classical computers. Okay, so log 2 give you 1, log 4 give you 2, and you have 2 terms, so multiply by 2. And so it's a very simple calculation that at the end of the day, you got 1.5 bits. Now I ask you, if you want to code these events, how are you going to do that? Well, this is not very hard coding problems. You might come up with the following smart ways. That is, I'm going to just code A with 0. That is, when I type 0, that means A's. And I'm going to code B and C as 0, 1, and 1, 0. Okay? And if you code it this way, let's see that on average, how many bits do you need to transmit all the event information for this random variable? Well, that's relatively simple. With probability 1/2, you just need 1 bit, right? With probability 1/4, that you need 2 bits. With probability 1/4, you need 2 bits. So that is basically half of the time you need 2 bits, and half of the time you need 1 bit, and that average to 1.5 bits. Okay, so I'm talking about the smart way. there's always a very dumb way to code the random variables. You can use many zeros to code A, and many 1 zeros to code B, and many 1 0 1 0 to code C, as long as there are 3 different binary codes, right? And of course, then you can take up lots of computer time, and that's not surprising. This is commonly in use. Think about this. If all the codings in your computer is automated, that is the smartest encoding in information theories, then there's no room that you can compress them, right? The fact that you can compress them means you're using not so smart encoding. You're using convenient encoding scheme instead of efficient encoding scheme. Wow, great. So now you see this very interesting coincidence, right? You have random variables with different probabilities and 3 different outcomes. You calculate the Shannon entropy, the information entropy H. You got 1.5 bits. It turns out a smart ways of encoding or coding these transmitted informations also need 1.5 bits. And is this a coincidence? Well, it is not. It is not. This is one of the most beautiful theorems that Shannon has put down back in 1948. 1948, well, okay, it's actually not that far away though. I mean, right now we're at 2022, right? 2022. So, with this said, so what does this noiseless coding theorem says? It says the information entropy Hx, we just learned, is the lower bound of the number of bits needed. Okay, it is the number of bits that you need to what? To transmit the states of a random variable x. Wow, this is something definitely non-trivial, right? So what does this information entropy means? It means that is the minimum bits you need if you want to transmit the random variable, the outcome of the random variables faithfully. This is highly non-trivial, okay? And surprisingly, somehow, by asking not what this almost like completely different questions in science, you come up with the same entropies. I think that's one of the really amazing part. And the reason for that is the following. If you really dig into the technical details of the thermal and statistical mechanics and ask yourself, what is the core approximation in statistical mechanics? Then you will realize it's not partition function, it's not temperatures, it's not heat. It is about how we deal with statistical information in the system. And it is entropy. And that's why that these two branches of science can be combined together. Does A equal 0 mean A event happens? A equal 0? No. I'm sorry. I may be running through this too fast. This is what we code different things. On classical computers, we use binary code to denote different things. So when I make an observations of the random variables, it might come up with A, might come up with B, it might come up with C. Then I can write it down in binary code. So for instance, I can write the outcome A as 0. It does not mean A equals 0. No, it doesn't mean this way. And when B happens, I denote this as 0, 1. And when C happens, we denote it as 1, 0. And this is commonly used in modern times computer. For instance, you use ASCII codes to just express all the alphabet that you encounter in the typewriter. Okay, it's just a different way of using binary code to express different events. Thanks for asking this. And so here we come to the second example. Ta-da! That's the binary entropy. And I hope this binary entropy will sort of wash away some of the confusions that you would have, and also the distinction between information and the information entropy. They, of course, are rooted in the same understanding, but their trend can be rather different. Suppose now I have a Bernoulli random variables. Okay, I have a Bernoulli random variables. So the Bernoulli random variable just have two outcomes. Let's say that x equal to 1 and x equal to 0. And the probability for x equal to 1 is labeled by a parameter, sometimes called superparameter, p. And if I then try to write down the information entropy associated with this binary random variable, and this is what you got. Because for one outcome minus log p, and it's weighted by p. Another outcome minus log 1 minus p is weighted by 1 minus p. And it's straightforward that you can just plot hx. And this is what you got. So there are two interesting things. First of all, if you look at this part and this part, that is when p is almost 0 or p is almost 1, what happens? Well, you find out that this hx is almost 0. Okay? So this is surprising. If you think about the information, when p is 1 or p is almost 0, that means that one outcome almost almost become definite. It will almost appear, right? Just like the sun will rise to this level, where the complementary event will become a rare event, which is almost like the lottery numbers. So you might think, come on, how can the average outcome to be 0? Well, the fact is this, that when p is, when p is really small, log p diverges, but then it's weighted by p, and this p goes to 0, much stronger than how log p diverge. And thus, for small probabilities, the average information that you will get out is actually negligibly small. So then there are two different ways of looking at this whole thing. Yes, rare events do give you lots of information. But rare event, if you're talking about the average information you can get out, it turns out for routine materials like sun will rise tomorrow, this sort of things, it doesn't contain lots of information. And even multiplied by p almost equal to 1, just still give you a small number. On the other hand, for truly small, rare events with vanishingly small probabilities, because it almost never happens. So that information, weighted by the probability, is still small. I think this is philosophically interesting, isn't it? The fact that this p equal to 1 and p equal to 0 all goes down to 0, that means the anticipated information conveyed to your brain is small, meaning that something happened routinely doesn't really make you wise. And also, something really happened in your life, even if it happens, it also doesn't educate your brain that much. What you can learn most from this is actually when the random variable becomes uncertain. That is, it's neither 1 and it's neither rare. So of course, with this binary entropy, it's symmetrical, okay? And because it's symmetrical, it's not very hard to guess that once you know that these will eventually dive down to 0, so then for p equal to 2, that's where it reaches its maximum entropies. And I will leave it with a very interesting thing. Is this another coincidence that this information entropy turns out to be just 1 bit? So if I give you a Bernoulli random variables, then the maximum information that you can learn from a Bernoulli random variable is just 1 bit. It's simple, but you should think about that. So once you know this, then you know once we not just looking at a particular event, but looking at the probability distributions, knowing probability distribution is not just one event. It's a bunch of events with probability add up to unities. So what should we then develop our intuitive understanding? That is, the information conveyed per message, per measurement, is basically the uncertainty, okay? It's the uncertainty of the probability distributions. So either P goes to 0 or P goes to 1, will make the whole situations more certain. And that doesn't really convey too much information to you. So that is the part that I try to explain. There's a very important concept that information entropy, Hx. Once you know the probability distribution, you can calculate it. And we have 2 examples. One example is how much bit you need to convey a random variable. And there's a very beautiful and strong theorem behind us. And I also give you a binary entropies, and hopefully that sort of give you this very important intuitive understanding. That is, the uncertainty associated with some probability distributions is basically equal to the information conveyed per message or per experimental result. Okay, so I got another question. Let's see whether we can do something more. And yeah, I think this is a pretty smart question. What if I convey A equal to 0, B equal to 1, and C equal to 0, 1? Oh, that's a good one. That's me. Yeah. If you encode it this way, it seems that that's smaller than this whole thing. So let me mark this down. Yes, that seems to be a counterexample of the noiseless coding theorem that you can encounter in Shannon. That's a good question. So I don't know the answer at this point. Is it different let me do a transition here. Is it different for defining information in quantum computer, although it hasn't existed yet? Well, first of all, quantum computer does exist. It's just not come to your life with practical information at this point. So that's the first thing. The second thing is that yes, the information in quantum computers with quantum algorithm is defined slightly differently. It's associated not with the probability distribution, because probability distribution is L-defined in quantum mechanics. It's defined as the, let me just write it down. So let me switch it back. Okay, so I got a page here. So that's basically, you can define a relatively similar concept that's called von Neumann entropy. And for von Neumann entropies, it defines this quantum information as minus trace rho log rho. And then this rho here is just the density operator in quantum mechanics. Okay, so that would be this one. I think that's great. I think you guys are getting used to this YouTube live and start to asking real-time questions. That's excellent. Okay. So then go to the next one, the differential entropies. So the differential entropy is just a mathematical generalization. Then we try to generalize this very useful concept of information entropies to continuous random variables. And so sometimes later on, when I write down entropies, I might mean differential entropy or not. Okay, so basically they're just the same. If you just look at this, for continuous random variable, instead of having the probability functions, you have a probability density function, and it's a density. So it might cause some subtleties, and since with the time limits, I won't bug you with the minor detail, which turns out to be important if you are really doing relevant research on this subject. But the whole idea is the same. It's basically just taking minus log p as your information, okay, and taking average value of that. So then that will just give you minus px log px. So that's the hx. So that's pretty nice. So let me just give you one example. For instance, let's try to compute the differential entropy of the Gaussian distribution. Know that the PDF, the probability density function, okay, the PDF is just this exponential form. It has a big exponential and it's quadratic here. And if you take a log and adding a minus sign, then you just bring this whole thing down and canceling out the minus sign. So then you got a quadratic function, so x minus q squared. And this constant will just give you some constant here. So if then you push forward, try to calculate this hx, the differential entropy. So that's minus log p average values. So you take average value of this, but then x minus mu square average value is the sigma square. That's the definition of variance. So then that's the first term you got. The second term is the constant. Taking average value is still the same things, and you can pull out the square, and so then you can put 1/2 here and then square the argument here, so they become 2 pi sigma square. Combine both terms together. The first term give you 1/2. The second term give you 1/2 log 2 pi sigma square. So after finish this whole calculation, so that's quite interesting. It just tells you that the average information you got by detecting the Gaussian distributions is log sigma. Okay, that is just the standard deviation, log standard deviation, and that sort of makes sense, right? If the Gaussian is really sharp, then everything pretty much occurs with the means. So there's no surprise. There's no information conveyed by the measurement. But if the sigma is large, then your probability is broader, right? And so then when try to do the measurements, you might get something deviate from the average value mu significantly. And thus, you can actually gain some information out of these not so trivial events. Okay? So that is the result that we're going to use in our next videos. So please keep that in mind, that now we know how to calculate the differential entropy of the Gaussian distributions. And here comes the real meat of these videos. So it's written in all red. I hope that doesn't hurt your eye. That's the maximum entropy principles. So that's how it reads. When an inference is made on the basis of incomplete information, that is, when you're trying to make prediction out of incomplete information all the time, right, in your life, it should be drawn from the probability distributions. So since it's incomplete information, so you cannot know something for sure. So you got to follow some probability functions. And what is the correct probability function you should choose? Well, it turns out you should choose the probability distribution function that maximizes the entropy subject to the constraint on the distributions. That is says, collecting all your prior knowledge before doing the measurement. And if that is the maximum content of information you know, most likely you maximize your entropies, and then you will find the correct probability distribution associated with that. This is probably a little bit abstract, so let me walk it through concrete example, so then you see how it works. Okay, and here we got new questions, so I will take a brief break and then try to respond here. How can we relate von Neumann entropy to the Shannon entropy? That's a good one. Basically, if you choose the eigenbasis, sometimes the probability densities can be diagonalized. And if the probability density can be diagonalized in its eigenbasis, you write down the von Neumann entropy and the Shannon entropy, that would be the same. But in general, they are not the same. So the Shannon entropy is a classical concept, where the von Neumann entropy is a quantum concept. And so I think this is a really, really good question. Let me just take a very simple example. Suppose now, I have a hydrogen atoms sitting in its ground state. So in terms of von Neumann entropy, the density operator is relatively simple. So it has probability 1 sitting on 1s and probability 0 everywhere else, right? So if you then computing the corresponding information entropies, that is 0. That makes sense, right? Because you know the ground state for sure. But then if you then take the eigenbasis, in this case here is the Hamiltonian, right? So you take the energy eigenbasis, and then it has a classical corresponding probability like P1s equal to 1 and all other probability equal to 0. You calculate Shannon entropy, you still got 0. So that's the case where the von Neumann entropy and the Shannon entropy equals each other. But unfortunately, in quantum mechanics, you can break down, right? Even though that you know your wave function is in 1s, you can try to look at this simple system in a slightly different way. Let's just take, for instance, the very popular basis in popular science, that's the coordinate space. Then you have the probability distributions of the coming up from the wave function, right? You can calculate probability densities that where the electron will appear in the whole space and everything. And in that basis, you use the probability appears at different locations as your probability density function, and then you can calculate the corresponding differential entropy. And I can tell you for sure, because you don't know where the electrons are, right? So then you got non-zero Shannon entropy. And in fact, that these two perspectives are related by unitary transformations in quantum mechanics, so they shouldn't give you any different results. But Shannon entropies give you different results, okay? So Shannon is a genius, yes, that's right. But then the devised entropies are only applicable to classical communications. So with quantum mechanics, you need to relearn this whole thing, and then resort to the correct definition of quantum entropy. That is also known von Neumann entropies. I hope this sort of explain the puzzles. Okay. Oh, I thought that I'm switching, so I forgot to switch. In any case, so let's go back. Sorry. So I'm leaving on the maximum entropy principles page for so long. So first one, let's see how Boltzmann distribution come out naturally. Let's just take a very general case here. Suppose I have a statistical system, and of course I know the probability should integrate to 1. Okay. The second thing, suppose now I also know some other thing. It could be the particle number, it could be the energy, it could be some other things. Let's say just in general, some GI, some constraint. And the expectation value of that equal to some constant alpha I. And even though that I don't exactly know the details of the outcomes of the probabilities, I know the expectation is held fixed here. So how are we going to do that? If I want to maximize the entropy with a constraint like this, okay? This constraint is intrinsic for probability. This constraint is just the actual information that you know. It might vary with specific physics or chemical questions. Okay, so how are we going to solve this? Well, we're going to use the well-known Lagrange multiplier methods. That is, we are going to minimize H star instead of H. So this is the differential entropy, and this is the probability conservation. And these are the actual information that we know from gauging the average value of some particular G's. Okay. And once you know this, how are you going to do? Well, that's really simple. First of all, let me remind you, if you take a partial differentiation with respect to lambda I, then you will get back the constraint. That is this term and that term. And if you are confused, you can go back to the prime mathematics and then sort of refresh with the Lagrange multiplier method. And of course, the important thing is take the functional derivative with respect to p, which will then take out the integrals and then give you this very nice result. Basically, we're dealing with minus p log p. So when you take differentiation, taking p out, you get a minus p. Taking log p, you get 1 over p, that cancel out, give you minus 1. And this term doesn't matter, it's a constant. And taking this out, then you get lambda 0. And taking this out, you get lambda IGI. So this is actually relatively simple. By maximizing the entropy, the information entropy, we then get the probability distribution, which is just exponential. Lambda 0 minus 1 is still just a constant, okay? And also the associated constraints, summation I lambda IGI, and these lambda i's are just corresponding Lagrange multiplier. So applying to the Boltzmann distribution, it basically means that if I have a statistical system, it follows some probability, so the probability adds up to 1. That's always there. But in addition to that, I also know the probability series has a specific average internal energies, okay? So that means the constraint is E. So if you just plug it in, that would just give you the probability distribution should take this form. So this is just some constant. You can write it out. And this is an exponential dependence on energy. And if you work out all these whole things and then I write it in a more convenient and familiar forms, then you find that this is 1 over z and this is minus E over kt. Basically, this lambda 1 here is minus 1 over kt. It's the reciprocal of the absolute temperature. So now you know the absolute temperature is nothing but the Lagrange multiplier of energy conservation. So if you have a statistical system where its average energy is fixed, and you try to maximize the entropy, that is, you try to erase all other information contained in a statistical system, this is the distribution you get. So whenever you get something which is a Boltzmann distribution, that pretty much tells you two important things. The first of all, the system, the statistical system that you encounter, it's not very smart. It's inhumane. It's just contain basically not much information. The second thing is, whenever you find a Boltzmann distribution, that means the average energy of the system is held constant. So let's say that just means that an average energy of the statistical system play a crucial role. And in addition to this very precious information, we almost know nothing about the statistical system. So that's cute, isn't it? And so this is actually how you can understand the well-known Boltzmann distributions in modern information theories. And what's more is that try to remember science does not only contain the branch of physics, okay? Physics may be fundamental, but it has tons of other applications as well. In particular, information is such a fundamental concept. So right now, let's just assume that the prior knowledge, that is the knowledge we know in advance, it's very simple. Suppose now that I'm dealing with some probability distribution, I only know the means and I only know the variance. So what does that mean? That means that even though I don't know the probabilities, but I know that if I calculate x minus mu squared, it goes to sigma squares. So this is actually the situation that you often encounter in data science. Okay? And so what would be the ultimate probability distribution function to use that would maximize the entropies? Well, again, since we have derived the formulas in general, you just plug it in, because now the constraint functions is just x minus mu squared. So then this is something that you got. Again, this is a constant, and then this parameter you can just work it out. And here I'm just working it out for you and writing it in a more familiar way that you will find. And this is nothing but the Gaussian distribution. Wow. So I hope now you have a better understanding about Gaussian distribution. What is Gaussian distribution? Gaussian distribution means someone's knocking on the doors of our house. Gaussian distribution means if you only know the information of the mean and also you only know the information of the variance, then the ultimate probability distribution is Gaussian distribution. This is an alternative way that how you can actually understand the central limit theorems that we just talked about, isn't it? Right? So the central limit theorem can also be viewed as a direct consequence of maximized entropy principles. Okay. Well, okay. Some mathematicians probably don't like this because some mathematicians saying that no, this is not the same. Show how start the bullshit. Oh, okay, I will cut the bullshit. Yes, central limit theorem is a theorem that you can prove where the maximum entropy principle is a principle. So of course it's not a proof. But I'm trying to tell you, if you think about this in an intuitive way, that you have a bunch of random variables, you sum them up, and during taking all the limits, right, the means and the variance are always kept constant, and you have no other additional prior knowledge about the probability distribution functions. Okay. Then the most likely answer that you can get is just the Gaussian. Okay, it's not a proof, but it's a very, very beautiful demonstration that how maximum entropy principle works. And some of you kindly noticed me that there is earthquake and also translated into Mandarin 地震. Oh, great. Really? Is there earthquake? I didn't feel it. Sorry about that. Probably too excited about the material we are covering at this point. Okie dokie. So I hope that two examples, one for physics, one for information science, sort of wake you up about the maximum entropy principle. Since I'm running out of my tea, so I'd better wrap up for the remaining materials. But am I going to? Yeah, yes, okay. So at the end of our course, I'm going to introduce a very important concept that's called Kullback-Leibler divergence. In short, it's typically called KL divergence. Okay. So suppose now I have two probability distribution functions, P and Q. How are you going to measure the difference between these two? Smart guys, Kullback-Leibler come up with the idea. Okay. So it's written as P double bar Q. And the reason why we use double bar that you will see later on, that is because the KR divergence is not symmetrical, it's not a distance. So since you want to really find the difference between two probability distribution functions, So why don't we just compute the information content of each single event and subtract them? So then I know how to do this, right? Well, but then there's a little tiny and the difference of the information can also be written as log p over q. And it's trivial if p and q equals to each other. Log 1 is 0, so taking average of that, it's just 0. But there is a one important subtlety. What exactly is the average that you performed? Okay, so try to remember here when we write it this way, this is the p double bar q, that's the Taylor divergence of between p and q. That is defined this way so that when you write it down, it contains two terms. It's the average value of log p minus the average value of log q, but the average it performs on the probability distribution p. And in real applications, p is often the ground truth. That is something that you are seeking. And q is the trial function from the neural network machine learning that you got, and then you try to compare. And so then you can try to minimize the K-L divergence to find the optimized solution. Sometimes you may not find exactly q equal to p, but you can minimize this K-L divergence so that you find the closest answer to the ground truth that you would like to achieve. And also, one can actually use the log properties. The log has a specific curvature property, and you can actually show that the K-L divergence defined this way is always positive. Or sometimes it is also known as Gibbs inequalities that you can find. So the proof is relatively straightforward, just mathematics, so then I won't bug you with you at this point. So one important thing that I want to demonstrate with the K-L divergence is that it is not a distance. When we talk about distance between 2 points, the distance between A and B equal to the distance between B and A, right? That doesn't work for K-L divergence. Why so? Well, just write this down. This is the K-L divergence P double bar Q, and this K-L divergence Q double bar P. And one is weighting over P, one is weighting for Q, and this is log P minus log Q, and this is log Q minus log P. And please be careful here. You might think, aha, if this is positive, then this is negative. If this is negative, then this is positive. And since it's positive, so then one of them is not going to be positive. Totally wrong. Please. There is an integration here. So you can actually show both K-L divergence are positive. Okay? I'm just writing it down with this confusing minus sign problem. So there is no problem at all. So for this one, I'm basically measuring the information distance weighting over px. What does this mean? That means when p is significant, I'd better minimize this. On the other hand, when I'm measuring q double bar p, I'm calculating the difference between the information one more time, but then weighting with q. That means if q is significant, I'd better have this minimized. And because in real operations, q and p might not be exactly the same. So then minimizing K-L divergence of this form and minimizing K-L divergence of this form may lead to different answers. So this is a very important inequality, saying that K-L divergence P double bar Q is not the same as Q double bar P. Okay? Good. That knows I'm just going to show you a very interesting example that you will find in this very interesting textbook. And yes, I know last time when I tried to show the book, you reminded me that I better switch the... So that is this big book on deep learning, a very dreamy cover, right? So this book is written by good fellows, Benjel and also Kerville. three very important computer scientists in this field. And so if you frustrate through, then you will find relevant chapters on the KL divergence. And you will find these interesting examples. So let me walk you through with this very interesting example. First of all, suppose now your ground truth is a double peak PDF. Troublesome, okay, the twin peak problems. And since you really hasn't catch up, so you write a program and try to optimize the difference between that one. But the one that you are using to fit that is a Gaussian with variance mean, mu, and sigma squared. So you know you will never reach the correct answer, right? But with the definition of KL divergence, you can try to, even though you cannot get the correct answer, you can get what we call the optimized answer. That is the answer with minimized KL divergence. By the way, divergence just means deviations. And because most physics students learn divergence through del.v, so you might think, oh, there's no divergence here. Divergence in English just means the differences. Okay? So here, let me try to first use the normal one. This is the most common one, the KL divergence you use. That is P double bar Q. That is, I'm using the ground truth as the probability, and then I'm checking the answer and to see how good the answer can be. And if you write a program, you really can write a program and run it, and the optimized answer is the green curve here. And the ground truth is this double peak. You might burst into laugh. Show how. In what sense? This is the best guess to the double peak. Well, that depends, right? First of all, it reproduces the symmetry. Symmetry is important in physics. And second thing, you might think there is a huge deviation here, but that is okay. Why? Go back. I'm measuring the difference between log P and log Q. But if P there is small, that is fine. So this is almost like when the boss is not checking, that is rare events, you can take your vacations. So the deviation can be safely disregarded. So this sort of things, because you base on the px. So when px is significant, you hope the qx more or less follow it. So the best you can do to fit a two peaks with one peak is this non-trivial answer here. And in fact, this corresponding to thermal statistical mechanics is what we call the symmetrical solutions without spontaneous symmetry breakings. On the other hand, we have another set of approximations. That is, what about instead of minimizing the KL divergence P double bar Q, we minimize the KL divergence, the Q double bar P. So the major difference is right now, you are weighting the deviations by the trial probability that you put in. So what does that mean? That means as long as I can keep the deviation small, okay? I can keep the deviation small. When Q is not 0, then I will get a pretty good result. And if you really write a program to run this, you will run into two possible solutions. And so here I'm just showing the left solutions. Equally well, depends on the initial condition and the detail how you code this whole thing, it might relax to the right as well. So you can see why this minimizes the KL divergence of Q double bar P. You might think there is a huge peak, it's completely ignored, but you don't care, right? Because the QS here is almost 0. So the deviation here is weighted by 0, so then you don't care. But on the other hand, for the part you care, then you try to do a pretty good fit. And because you have two different ways of fitting this and this corresponding to the spontaneously symmetry breaking state, which are also important. in thermal and statistical mechanics. So you can see here, different types of Carroll divergence lead to different answers. And it doesn't really mean that which one is better. It really means that which question you ask. And with specific type of questions, then one type of Carroll divergence is better than the other type. And so for this type here, the optimization really follow. If you think about the ground truth at the both, that you try to, well, when you try to execute something, so right, you try to optimize the difference between what both means and what you try to do, and that is the Carroll divergence that you try to do. On the other hand, this is a more creative way. That is that you try to optimize the difference between your both comment, even though you just take half set of the comments, and since you ignore the other half, and once you ignore it, you don't care about the differences. So in Mandarin, we have a very good ways of describe this situation. It's called 自我感觉良好, isn't it? And while teaching, this also works. So suppose now we have like Twin Peaks students in our audience, and some professor will choose to target the top performing student, whereas some other professor will just target on the underachievers. That depends on, that depends on your personal taste. Where if the professors learn the Carroll divergence and try to really optimize the learning efficiency of the double peaks learning efficiency for the whole class, he might then target at some students which is basically not existing in the class at all. Don't you think this is really something inspiring when teaching? And I personally find that is truly so. And this Carroll divergence pays the cornerstone that how we are going to talk about the mutual information, which we will air out soon at around 15 o'clock. No, in terms of that, I should say just 3 o'clock in the afternoon. So stay tuned. We'll come back at 15:00. Okay. So these videos that I would just end the YouTube live streaming here. And if you have any further questions, just leave the message and then I will try to respond. Have some fun. Bye.